Okay, so thank you very much for having me here in Tallinn. It's a great pleasure to be back. Okay, so in this lecture, I was trying to somehow explain a bit of like the circle of ideas around the problems of deforming K-theory classes or average by cycles if you are lucky in particular cases. So somehow, let me start with introduction and the spirit, or maybe the reason why one is interested in this kind of problems is to solve this question. So how to build new cycles from old ones. Okay. And the reason why interested, what one might be interested in this kind of question is that algebraic cycles are notoriously difficult and complicated objects, and we're always very happy if we are able to construct algebraic cycles in a meaningful way. And if we are so lucky and so good that we build cycles in one situation, we would like to understand if we can build new ones starting from things we have already done, okay, to minimize somehow our effort. Okay, and specifically, the idea is try to use some deformation theory, and you will see that this will be interpreted in a very specific way to do so. Right? And in particular, we'll be interested today in the problem of deforming classes, in the adic direction, or varieties defined over ZP over variance of the verb. I will use the word classes to refer to cycle classes, as it said here, or more precisely to K-theory classes. Okay, so we'll interchangeably pass from questions starting from algebraic K-theory, specifically K0, to actual Charles groups. Okay, most of the time for me, classes will be K-theory classes. Okay, so let me start with recalling some ideas from Hodge theory. Okay, and this goes back to Podrodnik, and I think a person who deserves really a lot of recognition in this is Bloch, right? And there's a specific paper from 1972 in which most of his ideas were explained already. Okay, so here's the situation. So you have a variety in fixed vector notation. Let's say X, yes. So say X is your smooth and projective variety defined over a small disk, okay, a small disk. And we're working over, say, the complex numbers, just to fix ideas. And if you complete this in, let's say, at 0, you end up with something, I don't know, let's pretend there's something like this, okay? Which is smooth and projective. All right, so we have a variety. A K would be, well, let me just stick to the case A equals C. Right? So let's move the projective family like this, and isomorphism. Written this way by Katz, we call this isomorphism phi, relating the Drang homology of the central fiber, so the fiber at equals 0 of this family, to the homology of the family. Right? So let me maybe call S the family here, the base here. Then I have an isomorphism like this. I have HI, the Ran of S over S, and this isomorphic to the map goes in this direction, H have the Ran of the central fiber, so X0. Now, the important fact about this isomorphism is that this isomorphism is not compatible with the Hodge filtration on both sides. Okay? So, in particular, so mark, the interesting fact is that if you take FR of FI, the RAM intersected with, oh, sorry, of course, I forgot important thing. right? This is long over wide. So you have to take the horizontal sections with respect to the Gauss-Manning connection that you have with that. Right? So if you expect its cycles here to come from actually central fiber. Sorry, that. Yes.
X0, what we're supposed to get on the right?
Sorry, say again. Yes.
What is X0?
X0 is the central fiber. So the fiber of Ft equals 0. So T equals 0 here, and you have X0. Okay? This would be my notation throughout the talk. So thank you for your question. All right, so you can ask this question. So you have Fr Hi intersected with Hi equals 0 of your family. Okay, and this is in general not the same thing as Fr Hi of X. Okay, so this means that if you start from a class here, which is of Hodge type, so for example, is a class which comes from an algebraic cycle, and you know that the Hodge conjecture is exactly about detecting cohomology classes and understanding when the classes are actually coming from algebraic cycles, then the condition of being of Hodge type here translates into a non-trivial condition on the left-hand side if you take into account the Hodge filtration on the left-hand side, okay? Because precisely this is not an isomorphic or filtered vector spaces if you take the Hodge filtrations on the left and the right side. Okay? So in other words, if I start from a Hodge class here, it's not at all clear whether this class is going to be a Hodge type here. Okay? All right. So maybe let me just say this is the remark. Right? If alpha is the class of an algebraic cycle in the RAM, then Hi the RAM X0, and therefore it's of Hodge type. Okay, then phi minus 1 of alpha might not be of Hodge type. Okay, so being of Hodge type in this case means that you are, this is, well, should rather say 2i to be reasonable. Okay, so Hodge type means that you are in Fi H2i, and if you take F minus 1, phi minus 1 of alpha, it's not clear at all whether this class is going to live in the Fi 2i of the Drunk homology of X over S. Okay? So motivated by this observation, then Grothendieck made the following conjecture, which is the deep conjecture, and is a form of the Hodge conjecture. Okay, so if I start from class psi in K0 of the central fiber, so that's 0, right? Q, such that, right? I start with the class here. I consider the Chen character of the same. Okay, so this is a way to transport a class. All right, so I suppose that you all know that this is isomorphic to Charles star at 0. You, right? I mean, it's an isomorphism of rings between the K0 of X0 and the Chow ring of X0. Like the Ram-Chen class of Xi, this will live in the sum of H, Y, the that's 0, okay? Right. And the condition is, the conjecture is the following. So if, right, and only if, in fact, I minus 1 of the Ram-Chen character of Xi, if happens to be of Hodge type, so is in the direct sum of Fi H2i of the RAM, and this time I'm talking about model, okay, then there exists a class in K0 of X such that the RAM class of this Xi bar is equal to the required class. And in fact, this class is lifting my class sum.
So do you mean that the Chen class is in that direct sum?
Sorry?
So do you mean that this Chen class is inside that direct sum?
That's absolutely.
Yeah.
Okay.
So this is an extremely deep question, right? Because I'm asking for basically a version. So this is version of the Hodge conjecture, as you can clearly see, because it's about the existence of a cycle starting from an actual the drum class. And the drum class is actually built from the class in the special fiber, right? So you start from an algebraic cycle in the special fiber. Okay, you take the drum homology, you look at the image there, you lift using the isomorphism, you impose an extra condition. And the extra condition is the only condition which makes sense to us, namely that the class is of Hodge type, and then you guess that this class itself is a class of an algebraic cycle. Okay? Sounds easier than the Hodge conjecture, is not. Okay? Because you start from an algebraic cycle, right? You have an algebraic cycle on the special fiber, and you ask for the existence of a cycle lifting. Okay? So sounds slightly easier than the Hodge conjecture. Okay, the fact that we don't know anything about that tells you it's not easier than the Hodge conjecture. Okay, basically, and we only so I guess we know very little about this. Okay, so we know, I guess we know this 4 line models. Okay, but let me go back to this specific situation later. Okay, so motivated by this, then the adic variant of this question was posed, and this is due to Fontaine and Messing. By the way, this conjecture usually goes under the name of variational Hodge conjecture. And Fontaine and Messing formulated the p-adic variational Hodge conjecture. The situation is, of course, of arithmetic type, right? So you start from x over, say, OK. Again, it's smooth and projective. Oh, just with its ideas again. And OK is a mixed characteristic DVR. And little k will be the residue field. Perfect. Okay. Let's see what else. And OK will be complete. To mimic the situation working over the power series of events. Okay, so you have a family over the complete DDR, and then you try to ask a similar kind of question. And in order to ask a similar kind of question, you need to have the analog of this isomorphism to begin with, and that's provided by Berthelot. Explained that, for the use of Grothendieck again, that the Dirac homology of the generic fiber of your variety, so it makes sense. This Hilbert square, okay? So x over k is your model, so it's smooth projective model, then you have an xk smooth and projective, yes. Then you have x over k, this will be the generic fiber, okay? It's a nice variety over a p-adic field. And the isomorphism, so the statement is that the Dirac homology is isomorphic to crystalline homology of x0 relative to the bit vectors, provided you extend scalars. Okay, so crystalline homology will naturally give you a WK vector space, so you have to extend the scalars from WK to big K. Okay? Big vectors, of course, sit inside the big field K. All right, so then that the crystal CH crystal of the crystalline character, so it's a map, it's a ring map from A0 of A0 of x0 to the crystalline homology of x0. Then the conjecture is the following. So again, start in a class, okay, such that, okay, now you don't even have something to guess, right? I mean, there is no sort of obvious Hodge condition you require for classes which are in the crystalline side, right? These are first at the first approximation. But if you lift to characteristic 0, then this becomes much clearer, right? And here you can ask the condition that a class here is a Stadt, so is in the Fi of H2i. And if you expect that the class lifts, okay? So that if you expect the existence of a cycle, okay, matching the original cycle, here you go into right? Here you have Berthelot's isomorphism. Yeah, here I need to further extend space. Okay. Berthelot, right? Fine. Right. Then I need to live in Fi H2. Okay. And the question is if crystalline chain character of psi, if I apply this phi minus 1, let me call again phi this map, it is in Fi H2i, then there exists excited of the lifting. Okay. So this is the p-adic variational Hodge conjunction, right? And I hope I motivated enough the reason why it is called the variational Hodge conjunction, and it is p-adic because, well, we're working with p-adic variables, right? We are working with p-adic. All right, so what do we know? Not much. That's good for us, because if you don't know much, then there is a lot to do potentially, right? So you don't like problems which are completely solved, all right? I guess maybe we do, but only if we are the ones solving them. So okay, no cases. Huh? So basically, the only thing we know in this generality is due to Berthelot and August following a suggestion by Bellini, and again is for x. Well, it's for line boundaries. Okay, so you have a peak of x inside A0 of x. Okay. So classes coming, so line bundle classes, they restrict to line bundle classes, and you can ask the same question for things coming from the Picard group. In this case, you just end with, you end up with classes in H2, and you look at the first chain class of your line bundle. That's completely, so the geometry in this situation is captured by that piece of information. Okay? And if you do a bit of information theory, then you can understand what is the obstruction for lifting classes in PIC. Okay, so the reason why this makes sense and this works is because Picard, well, this specific piece of K0 has a homologic interpretation. Okay? So PIC is H2O X star, and this is very useful. Right? And you don't have this kind of interpretation for classes in other classes in K0. So you need this, okay, you need homologic interpretation for the Picard plus a bit of deformation theory, and which is not very hard actually. And the key ingredient, another key ingredient, is the following. Is the fact that if I denote by x the completion of x at p, or at pi more generally, pi, say pi in OK is a uniformizer, then the Picard of x is isomorphic to the limit over n of the PIC of x mod pi to the n, which we could call the Picard of x, right, for former schemas. This is Grothendieck's algebraization theorem. Grothendieck. I like to call this Gaga, former Gaga for thick. Okay? So, this fact, the way this proof goes, tells you that it is conceivable to split the problem into. So this is due to block, what it gets. We are just give you ideas about the timing. We are in 2012. Okay. So the idea is that one should split the problem into two parts. So split problem as follows. Okay. So look at the following diagram. You have so K0 of x Q. This is where you want to construct classes. Okay. Here you have K0 of x0. This is where you have classes, and in between you can consider a factorization through the K0 of every thickening of a center of a special fiber of your pen. Okay? This is nowadays denoted K0 continuous of the former schemats. Okay? It's a consequence of a series of non-trivial results, including Clausen-Scholze and Efimov, but this is indeed K0 of a suitably nice category of modules over the suitably constructed non-Archimedean space. Right? So it's a difficult object, but if you don't want to think about the difficult object, you can just use this definition, which works well for what I'm going to say. Right? And then, so do we have colored chunks by any chance? No, we do. We don't. All right. So anyway, so you can look at this factorization, and you can try to split the problem into two parts. So the first part is to construct formal liftings. Okay, and the second problem will be to algebraize the result. Okay, so that's the idea. And today I will completely be focused on that side of the problem. So to construct classes in the continuous K theory of X, starting from classes in the K theory of the central fiber, because nobody has any idea of how to tackle the algebraization problem. Right? So as the algebraization problem is concerned, we are stuck with this. That's the only thing we know in this generality. Okay? It's not completely true. In fact, there are very precise and very nice results over complex numbers due to Bloch back in 1970s, okay, which are extremely nice, and they use the geometry of Hilbert schemes, okay, of several Hilbert schemes. Okay, so you have to do something extremely clever, and only Bloch could do that.
So connecting, this is connecting the formats to get by completion to the power series.
Yes.
To the
algebraic thing. Right. Exactly. So it's a problem. It's an algebraization problem. Exactly. Okay. So right. So I cannot say much about the algebraization problem, but I can say a lot about the deformation question. Okay. So the first part of that. Questions so far? Yes.
Maybe where the lift exists in the categories or all the level case zeros?
You're talking about the straight arrows or the squiggly arrows?
Yeah, probably. The
squiggly arrows.
Yeah.
I will phrase something in a suitably. I will phrase something in a way which probably is going to be less squiggly in a second. Other questions? All right. So, guys here. Okay. Maybe while I raise, let me add that. Okay. So I told you something about the characteristic zero situation, so that would be variational Hodge conjecture. I told you something about the mixed characteristic situation, the p-adic variational Hodge conjecture. There is also an characteristic P story which goes under the name of variational Tate conjecture, and the person to quote for that is Matthew Morrow. Okay, so we did most of the results. I think had probably the nicest result in that approach. Okay, so all right, so how to tackle this? So let me ask it for the second section. This will be Hochschild homology. And the Bayesian fiber square. We should probably call this the Lopino cat / Bayesian fiber square. All right, so this deformation problem in modern terms is solved by looking at generalization of the theorem of Dundas, Goodwillie, and McCarthy relating the behavior of direct theory along in salient pairs. Okay, so let me just say the result. So the theorem. So this form is due to then Mathieu, Matthew Morrow, and Thomas Nicolaus. So the generality is R is a commutative ring. You can phrase it for associative rings, but we don't really need here. And salient, or we can say something about the associative rings. So P, maybe not this, maybe not this much. Anyway, then there is a Cartesian square. Okay, so the Cartesian square looks like, say, K of R to be coefficients. K theory of R or P, yeah, the coefficients. And here you have, okay, two things that I will define, kind of define this. Okay? Essentially. Okay, so the square of this, okay, Cartesian square of spectrum. Okay, so all right. Okay, so it's K theory. Okay, K theory of R, K theory of R not P, and there are p-adic coefficients, which is like a delicate operation to perform, but let's sort of ignore this for a second. Let's just pretend we are canceling everything with QP. Okay, it's not quite that, but it doesn't really matter for the sake of exposition. What about the bottom line? Okay, so the bottom line is constructed by two invariants. Right? These invariants are derived from Hochschild homology. Right? So you might know what Hochschild homology is. So Hochschild homology of the ring R, okay, is defined as the derived self-intersection over the diagonal. Okay? It's a chain complex, right? It's basically a chain complex. It's defined as homotopy, whatever. So you take R tensor R, okay, that's a ring, the tensor probably to the Z, if you're interested in Hochschild homology. Take R tensor R, is a match from R to but from R tensor R to R, which is a diagonal. Right? You take the self-intersection, which means you take the derived tensor product of R with R over this, and everything has to be derived because otherwise you get something. Okay? So you get a complex, and the homology of this complex is called Hochschild homology bearing R. Now, this thing has a natural action of a unit circle, which you can see by recalling what S1 is in homotopical terms, and suspension of a couple of points, right? Point. So this gives you an action of S1, and therefore it makes sense to take the homotopy fixed points for this action. This would give you HC minus. Or you can do another construction, which is the Tate fixed point of S1, which is basically a fancy way to construct Tate homology, right? Or in the classical metastasis, right? So you know how to do Tate homology for groups, okay? And basically you can sort of pin this up to a construction which makes sense for the action of a group like this. Okay, so I will say slightly more about that later. So let me just say in symbols HC minus is equal to HH homotopy fixed point of S1, and HP is equal to HH K fixed points of S1. That's it. That's some construction. Okay, so this is a bit difficult to digest, but there is a theorem. So combining this with famous theorem, which is the Hochschild constant Rosenberg theorem. HKR. Okay. The Hochschild constant Rosenberg theorem tells you that these objects, as well as Hochschild homology, are controlled by differential forms. Okay. There are filtrations on all these objects. Those graded pieces are related to things which are like omega I. Okay? Omega I being the different killer differentials of our gradient. And
what is the hypothesis about alpha?
R is a commutative ring which is Enselian over P. That's it.
Oh.
It's extremely general.
And also this option.
The HKR theorem.
Again, do you need some other hypothesis?
That's much. Okay, so HKR is a theorem which. All right. So let me say that in order to get an actual decomposition, you need to have smoothness assumptions. There are several ways to generalize this to non-smooth cases. But, anyway, it's the important thing to know is that this is a way to relate these invariants to differential terms. That's here. So, if you do this, then you get right. So, if let me write down statement. Okay. So, if x over OK, okay, my p-adic family is smooth, then you have the following, and maybe X is again the completion form a scheme. Then the following two effects. So HP of X over K, get coefficients, is isomorphic to product of our gamma deram of K gifted to Y. Okay, so that's the way to understand this term. Okay? Product over I. And HC minus encodes the Hochschild relation instead. So HC minus of X is isomorphic to product of field A derivative Y R gamma of X. Again, with shaped by Y. And so on homotopy groups, you get exactly the Fi H2I that I mentioned before, and here you get H2I that I mentioned before. So whatever these things, however these things are constructed, in the smooth case, they encode the round homology, and that's sort of a good generalization of these invariants in other contexts. Okay? Then you get, okay, so combining this with that, you get the following diagram. So you get that continuous K theory of X with p-adic coefficients sits in a Kullback square where you have K theory of the central fiber X0 again with p-adic coefficients. In fact, you can work a bit more and replace QP with Q. That's because these objects are sufficiently bounded P torsion, so you don't really it's not really a problem. And here you get these two terms. Okay, so here you get field I, field greater than Y, R gamma that shifted to Y, and here you get R gamma that shifted. Okay, so and the second is that is the Cartesian square. So how to read this? Okay, so saying that this is a Cartesian square means that you pass to homotopy groups and be careful about what you're looking at. You start from a class here, let's say K0 class. Everything is smooth, so there are no sort of negative K group subtractions. You have a K0, you have a class here, your cycle class. You look at this map here. I mean, call this map star, okay? Right? And then you, let's say that this class lifts, okay, to a term in F, a field I, H2I, which is exactly the condition we looked at before. Then saying that this is a Cartesian, means exactly that there is a class here, mapping to both, okay? So this solves completely the p-adic deformation problem, provided you understand what star looks like.
So star in when you have it's R the RAM for x0, right? And while the left hand side, you're
Sorry. No. It's the RAM of the only thing can make sense. So xk.
Okay.
Yeah.
It was on the left hand side.
Yeah, this is a xk. This is I wrote it there. Yeah. Mm-hmm.
So you're passing from the special fiber.
Right. So this map here has to be sort of understood.
Okay. Of course, you could have defined also for x0.
Well, I could, but then I would get something. Well, I could have defined some map, but that would be I could, but I didn't.
This is the theorem. This
yes. I mean, it's a theorem which you obtain by combining this theorem. Okay, so this theorem needs to be globalized. Okay, so you need to globalize this result, which you can do, meaning sheafify everything. These are sheaves, right? And when you plug in the HKR decomposition on the bottom line, okay, the bottom horizontal line includes HC minus and HP, and these two equivalencies are exactly what are given to you by the smoothness assumption. Okay, so the smoothness assumption is what gives you that you can split this gadget in these pieces. Okay.
Okay. But so when you say that it's Cartesian, it's so you have to define what is the star map.
So the star map is this map. So it was hidden in the existence of the square. So it's the same map there, which is very inexplicit at this point. Okay. So I get to you in a second about how you can make this more explicit, but it's a statement. Okay, so it's a theorem. Okay. So for the moment, so the map star. So since this is exactly what I wanted to say anyway, so the map star, okay, is the trace map. Okay. It comes from the cyclotomic trace, which is a general invariant, but the general thing you can construct passing from K-theory to invariants derived from Hochschild homology. Okay? So it's a sort of a very large family of approximations, kind of results involving approximations of K-theory with invariants derived from Hochschild and cyclic homology, and the map relating them goes in the domain of trace map. Okay? So it's the cyclotomic trace for the Hochschild and cyclic homology, is the Dennis trace for classical Hochschild homology, and so on.
This will be a local situation. That's what we are.
How is that local?
No, it's a Hessenian.
Yeah. It's a Hessenian along P, so it's not quite local. No, it doesn't have to be local. And then there is a globalization, there's a statement that which tells you that you can globalize this. So, and then.
Well, you pass to continuous K-theory in that.
Yeah, yes, right. So the point is that these invariants are defined on rings, okay? And then you can sort of define a continuous variant of all these invariants just by declaring that on a formal thing, they are defined as the limit of the thickenings. For K-theory, you're stuck there. So you just write what you get, literally the limit of a continuous K-theory, literally the limit of the K-theory reduction modulo P to the n. This is constant because it's on a special fiber. And then there is an observation, which is the fact that for invariants derived from Hochschild homology, then the algebraization problem doesn't exist. It means that these invariants are continuous. Okay? And the value that you get on a complete ring is actually the limit of the value that you get on the reduction model part of view. So there's an implicit statement here which identifies continuous periodic and negative cyclic homology with the actual periodic and negative cyclic homology of X. Okay?
So really, you advertise this by the idea of computing K-theory regression, which is it's a QP. So it's,
but
is that actually a what P thing, or is it honestly a rational station?
No. So I stated it with QP coefficients because it's easier, but you can actually work a bit more and put the Q here. Yeah. And the reason why you can put a Q there, it's because the P torsion is sufficiently controlled on these objects, and that's where the geometry kicks in. Right? Because these are, after all, smooth varieties. And you can control the torsion of this stuff. Okay, so you go that you. I mean, it's a bit of an argument, so it's not completely obvious, but you can. So and somehow, but you're using something on the geometry of variety. Not much, but you use something on the geometry of variety. Okay, so right, so the map star is the trace map, and this is maybe interesting, but you can identify it. Let me say on K0 with the composite phi -1 and the crystalline check. Okay, so it has a crystalline interpretation. So on K0, on pi 0, this map actually gives you back the map we were interested in. Okay, so it goes from K0 of the special fiber, goes to crystalline homology. You compare to the random homology, so you get the map, and the map is the same. Okay? So for this reason, then this solves completely the p-adic deformation problem. All right, so I can make the following remark, which is Bayesian, okay, and also AMMN. Okay? One can derive everything. Okay, so it has two suitable versions of derive the rank homology of that and get for any x in actually in Ki for any K group, right? That's not really relevant. In obstruction class, then we call it OX in H in sum of H R minus I of L omega x over L omega greater equal to R coefficient such that x lifts if no lift OX is equal to 0. Okay? Let's do continuous K theory. Now, the problem is that this class is a formal construction. Okay? It doesn't have any crystalline interpretation specifically, and it's something which pops out of this diagram if you just say derive. Okay? So you just formally construct something, and you formally end up with an obstructions class which you cannot control. Okay? And maybe the plan for the rest of my talk is to so my goal is to maybe use some logarithmic geometry to give class scientific methods to identify the class. Okay? So to identify the obstruction class and recover the crystalline interpretation. All right. So, right. So maybe it's the moment to have a 10-minute break. That's okay for you? No? All right. So, okay. So as I was saying towards the very end of the first part of the talk, the previous result. So that result solves completely the p-adic deformation problem in the smooth case, and I was saying that you can derive everything, which means if you are interested in what happens in the non-smooth case, or in bad reduction, which is what we usually do in you know, when we do arithmetic geometry, then you can get, this was an observation read in a paper by Baylinson and then was restated in the paper by Nicolaus. You can get some abstraction class such that, well, the vanishing of this abstraction class controls the fact that you can lift or not a K-theory class, but and then my goal would be to understand how to reconcile this construction with actual geometric input. Okay? So to understand this in terms of like the geometry of my family, and specifically give a crystalline interpretation as which was the content of this. Okay? So identifying this mysterious map which comes from the trace methods to something related to the crystalline channel. And so to do so, I need to say a bit about Kyoto-Kato homology. So okay, so here is sort of this is the general idea. Okay. You can say this in several sort of degrees of generality, but let me just start on the case where x over k is proper. This is not really necessary, but again, anyway, I'm interested in proper cases for my application, so straight to this. And let me suppose that it is semi-stable, okay? Okay, so semi-stable means that the special fiber locally looks like a bunch of hyperplanes in an affine space. Okay, union of hyperplanes in an affine space. All right. So the sort of dream or conjecture by Fontaine and Janssen independently was that there exists some kind of limit homology theory. Let me call it R gamma HK of X over OK. So limit homology theory in the sense of Hodge theory. Okay, so I don't know if you might or might not be familiar with the concept of limit Hodge structure. And the idea is that this thing, whatever it is, has to be the p-adic analog of the construction of Clemens and Steenbrink and Schmidt and Steenbrink on the limit on the Hodge structure. Steenbrink. So, right, so what are the properties? Okay, so it satisfies the following. So one, if X is smooth, so a good reduction, this thing is nothing but crystalline homology. Okay. Then, well, maybe let me just work with rational. Okay, so crystalline homology up to P torsion. But in general, I want this to compare to the rank homology so in general, I mean in the general semi-stable case. Okay, so this thing tensor with K has to be isomorphic to the rank homology of X. K. Okay, so this generalizes the Berthelot isomorphism between crystalline homology and the rank homology of my generic member of the family. And I say tensor with K because there's R gamma Kyoto-Kato of X to K is in fact an object in the category of K0 vector spaces. It's a complex in K0 vector spaces. K0 will be the maximum ramified extension psi K with the Frobenius and with the monodromy operator. Okay? So this object should come here. So these are complexes with Frobenius and with the map N, and it satisfies, so it goes from V to V minus 1. Okay? And on this specific object, the monodromy is in fact nilpotent. Okay? So it's a nilpotent operator. So conjecturally, this would be implied by the adic weight monodromy conjecture. So fits in Clemens Schmidt sequence, right? Which would be a sequence relating to the sort of homology of a singular special fiber and this gadget here by the monodromy operator. Okay? So in other words, informally speaking, the rigid cohomology of my semi-stable special fiber would be the fixed points of a modular operator on the Iodo-Kato cohomology. This is literally not true, but so an approximation of this statement is true. And it's true in low degree. Okay, so right, so this would be the analog of Berthelot's comparison theorem, right? From crystalline to. Okay, so this is a gadget. Okay, has a number of formal properties, and there are several instruction blocks. Okay, so instructions. So Iodo and Kato wants to name using crystalline methods. And nowadays there are sort of motivic methods. And there is a stacky approach. So the classical method is being sort of extended and pushed in many ways. And of course, there is work by Beilinson, Grosse-Klöne, Berkeley, Yamada, of course, Konez and Isiol, who worked in several degrees of generality on the Iodo-Kato cohomology. Motivic methods is something that I did with Martin, Callow, and Bertolzani. And the stacky approach is through the so-called Iodo-Kato stack, and this is, let's see, Anschutz, Lebras, Bosco, Rodriguez Camargo, Sure, Scholze, but I'm trying to remember if there is someone else before him. And Schultz. Okay, yeah. Probably 1, 2, 3, 4, 5. Probably 5. Okay. Thanks. Okay, so anyway, the theorem I want to advertise is following. So this is due to myself, Omiyundemo, Roberto Medici, and Park. And let's see, so X is proper, flat, over OK, with semi-stable reduction. Then there exists a Iodo-Kato Chen character. Maybe call it CH Iodo-Kato. So this goes from A0 of X0 to should I say, let me consider that. Product gamma so pay y, right? Such that plus psi nk0 x0 cube lifts to continuous K theory if and only if I minus 1 of the data that's psi is in field greater than y r gamma teran x of k y, where phi is the Iodo-Kato isomorphism. Okay, this one.
Sorry, when you look at the adic weight model, like between the classical and like the weights of the phi and module given by homology of the complex here. Like this is what you mean by the adic weight model.
Yeah. So the agreement between the weight filtration given by Frobenius action and the monotomy filtration given by the monochrome.
Okay.
Yeah. Okay. Yes.
Another question. Since we have a stacky approach, the Iodo-Kato stack, is there a version of the space and fiber square, but with the stacks instead of just the color theories?
I have no idea. So you would have to stackify K theory first, and I don't think we are anywhere close to that. As a matter of fact, I don't think we know that the cohomology of, the push forward from the Yodo-Kato stack to the point computes Yodo-Kato cohomology. So, as far as I know, this is not. I don't think this is stated in the paper. All right. Yeah. Okay. Right. Okay. So, how do you prove this? Right. So, and to prove this theorem, I want to give you some ideas from log geometry and maybe from multi-homology theory. Okay. So, right. So, what do I mean by log geometry? I mean, there are several sort of these two approaches on this. Classical, and maybe the only thing I will have time to talk about today. So, classically, and by classical I mean Fontaine, Green, Lucy, Capo, in any order. Okay. So, what is a log scheme? So, a log scheme is a scheme plus extra data, okay, to keep track of degenerations. Okay, so the local models are given by pairs, like this, where A is a commutative ring, and alpha is a morphism from M to A, where M is a commutative monoid, and this is the multiplicative monoid of a ring A. Huh? So it's a map of monoids, and that's it. Okay, so the sort of things can be arranged into a category, but this is obvious, right? I mean, morphisms would be commutative squares. You have maps of rings and maps of monoids, and you require the maps to be compatible with given arrows from the monoid to the ring. And maybe since we are in the 21st century, I should say that this category of, say, log algebras, or maybe pre-log algebras in the classical sense, so it's a category of pre-log algebras. So we have these pairs, okay, then just write A comma M, and it has this category has sort of strong, strongly trying to be presented generators. Let's see, it's correct, the adjectives. So as SFP, yeah, SFP generators, yeah, whatever, given by things like this. Okay, so strongly finely presented, I think. So these are like strong generators, so strong generators in strong sense. So this category are given by polynomial algebras. Okay, so exactly as polynomial rings over Z are the generators for rings, like commutative rings. These are the building blocks of a suitable derived theory for log things. Okay, so these are polynomial rings in a bunch of variables. You isolate some of them, and then you declare that you have a monoid, which is a free monoid, sending a basis to the coordinates that you are measuring. That's the only model you need to have in mind if you want to do the geometry, essentially, right? You only need to know the affine space to do everything else. All right, so some facts. Some facts about this sort of theory is that given to RP, so given a morphism, okay, in this category, you can define a notion of cotangent complex for this map, okay, which is an extension X of the cotangent complex of R over A, okay? And so this is obtained by animation from the case of polynomials. And in the case of polynomials, or more generally in a nice case, so this is like an extension, from omega 1 RP AM. And this is generated by symbols of the form dx for x in R. And then you require d log y or y in E with the condition that y d log y is equal to dy. Okay? This is a fundamental relation. Okay? So you're adding the form a symbol which looks like dy over. Right? That's why it's called logarithmic geometry if you want, because you're adding the d log of symbols. Okay? That's it. Okay. So after you have defined what a cotangent complex is in this context, you can define étale and smooth maps, right? Right, because you can make sense of deformation theory in this context. You can say that the étale map is going to be something for which the cotangent complex is contractible, and the smooth map is going to be something for which the cotangent complex is a projective bond with constant degree 0. That's it, right? So you can define this. Makes sense. And the remark is that a semi-stable family, it says family, is naturally an example of log scheme. Okay? This would be the globalization of this definition. Okay? So it means that you have to glue local charts together and you get something which is globally defined. There will be a logarithmic scheme, exactly as you form schemes out of a stack of commutative rings. And if you have a semi-stable family, you can naturally see this as a logarithmic scheme. With local models are then things like OK, right? Of say T1 Tn modulo product of Pi minus pi, right? That would be an étale model for a semi-stable family. And the monoid that you choose here is the form, again, n to the r, where r is the number of components that you have here, the product, okay? Sending ei to the variable ei.
So the special fiber is
Yeah.
just the normal crossing.
Yes.
And if we take any generic one, it's the generic one is smooth.
Yeah, sure. Yeah. Well, semi-stable family for me will be.
So yeah, the family is just the special fiber is log.
The special fiber will be
semi-stable.
It's a semi-stable, yeah, right. So in a semi-stable, like how locally I look like this, and then how locally I know how to define my log structure, and then I just glue everything from it out of coach. Okay, so maybe I should say that. Okay, so the remark is that this my semi-stable family, so my SS family, is not smooth, right? In the sense of classical abstract geometry, right? Because the fiber at pi equals 0 is singular, right? It's product of locus chi equals 0, union of chi equals 0. But what is crucial is smooth from a log point of view. Okay? And that's sort of the magic of log geometry, using the sort of expression coined by Federico. So things, they become magically smooth if you use some little bit of logarithmic geometry. Okay? So formally speaking, they behave like a smooth pattern, even though they're not geometrically smooth. And one can actually so smooth over what? Okay? Smooth over this thing. So let's recall that little k is OK modulo pi, okay? OK as a natural logarithmic structure. say 1 to pi, right? That's a nice morphism of monoids and goes to pi to the n. Yeah. But if you lose modulo pi, then you get a funny but still non-trivial structure, which is following. You get the composite map. So n goes to OK, goes to OK modulo pi, right? And the composite map sends everything to 0. Okay? So this pair, so a field with a monoid where every non-invertible element of the monoid is sent to 0, is called the log point. If you have enough intuition from algebraic topology, then you can imagine what could be the Betti realization for this object. And if you think long enough about it, you get a circle. Okay, you see that the topological representation of this thing is something like S1. So the idea is that the log geometry is encapsulating things like vanishing cycles. Okay.
Well, you can see as a point with the differential. Which from 0, that is yes, there's differential.
Yeah, you have a non-zero differential, yes, which is the circle, right? And that's exactly where the topological interpretation comes from.
The circle is the other.
Okay, so all right. Okay, so this is a very crash course on log geometry, but so we can define the log crystalline site. Okay, in which it's like a crystalline site, but in which you require the morphism to appear to be morphism in this category of log things. And there's a bit of sort of subtle, there are some subtleties in the construction. It's not really useful to go through them right now, but sort of beware that there is a way to make sense of a good notion of a crystalline site for a log scheme over a field of positive characteristic. Exactly as you can make sense of a crystalline site for a classical scheme over a field of positive characteristic. And if you embrace this definition, or you at least accept the fact that such a definition exists, then the Yodo-Kato homology of my semi-stable family can be defined as, for a proper semi-stable family, can be defined as the log crystalline homology of the special fiber at 0. And as you do for crystalline homology, you have to choose a lift, and that will be with PD envelope, and then you can choose bit vectors, and you can take, the log structure given by send 1 to P. Since I'm inverting P, doesn't really matter which log structure I'm taking on that one. Okay, so, right, so this is to tell you that this homology, for which I gave you a bunch of axiomatic properties, has a construction using crystalline homology or something related to crystalline homology. It doesn't really matter to know the definition, it is rather intricate. You can also maybe be happy to know that this specific homology groups can be constructed in several other ways, right? So whether using this stacky approach or using the monophilic approach I mentioned before.
Or the approach.
There is also a Hodgkin, yeah, right. There is also a Hodgkin approach, which, yeah, exactly as the crystalline homology can be constructed using the rounded form. So this was already in the Yodo-Kato original paper. Okay, so okay, so how is this related to what I explained in the first part of my okay? So the way you prove the p-adic information problem in the smooth case, right, was by contemplating a specific square. And this specific square involved K-theory. Okay, that's something we don't want to change. We're interested in considering classes in K0 or the special fiber, let's say, and to lift them to classes in continuous K-theory of our model. And then the bottom line of our square involved invariants built out of Hochschild homology, right? And then we use the fact that in the smooth case, these invariants related to Hochschild homology have a sort of Deriving interpretation, and this is sort of leveraged on the HKR theorem. Okay, these were the ingredients. When you plug things together, then you get this. So in order to somehow pass to the semi-stable carries, we need to fix the top part of the sphere and to change the bottom part of the sphere, right, involving invariants which see the geometry of the degeneration. And the way we want to see the geometry of the degeneration is by means of these logarithmic methods. So to do so, I need to find a variant of topological Hochschild homology and or general Hochschild homology, okay, which sees this sort of extra layer of complexity that I'm putting on my families by recording sort of a sheaf of functions which are going to zero when you use modulo p, modulo r. Okay, that's what's going on. All right, so recall that. Okay, I said this before. So if you have any commutative ring, then you can form EHH of A as, okay, so the derived self-intersection of your ring A, where if you want to do T, so topological, then the tensor products are over the sphere, okay, over the sphere spectrum. If you don't want to do anything topological, then you can change the sphere with Z, okay? So according to where you do the tensor product over the integers or over the sphere, which is now a deeper base in the, well, it's in the philosophy of modern mathematics, then yeah, you will get a different result. Okay? So if A M is now a log ring, okay, then, well, you need to sort of find some kind of analog of this construction which encodes this extra information. Okay, so let me try to motivate this by looking at this definition from a different angle, right? It's not really important if you work over the sphere or work over the integers. So to fix ideas, let's just work over the integers, right? So, okay, so what am I looking at? It's the self-intersection, everything is derived, okay? It's the self-intersection of a diagonal. Now, the diagonal, this thing here, has a very nice conormal bundle inside x times x, right? So I'm looking at things like x times x. Let me pass the geometry for a second, okay? You have a diagonal, so x will be step of A, right? And then here, I'm performing this x. And of course, I need to take the derived fiber product, otherwise I just get something stupid, just get x again. All right, so what is this encoding, okay? It's encoding the geometry of this embedding. So what is the geometry of this embedding? Tell me. Well, what is the normal bundle, the conormal bundle of x into x times x? It's I modulo I square, where I is the ADL, right? Which is omega 1. As we know from like the first community algebra course, when you construct the Kähler differentials, you can also define them in this way, right? Okay, so the definition of Hochschild homology encodes, in some sense, the Kähler differentials, and that was actually the reason why this was invented. Okay, so the reason why Alain Kohn came up with the definition of Hochschild homology, well, at the Hochschild problem, in this way, to have a non-commutative variant of differential forms, okay? Because this was encoding differential forms in the commutative terms. Right, so now we want to encode something which looks like logarithmic differential forms, because that's what we're doing. Okay? We are passing from classical differential forms to differential forms with logarithmic forms. Okay? So we need to have a geometric interpretation of taking logarithmic differential forms, which looks like the way you recover the differentials out of the conormal bundle of the diagonal. And this was an idea which appeared in the work and the masterpiece work by Kato and Takeshi Saito on Bloch's conductive formula. It's Kato, Saito. Okay, in which they realize that if x is equipped to the logarithmic structure, then you can do the following. So you just look at the underlying scheme of x. So forget the logarithmic structure for a second. You have the diagonal of x into x times x, And you can use the logarithmic structure here on X to do a certain kind of blow-up. Okay? So basically you need to add some denominators in the equation defining your X times X, and the diagonal lifts to an embedding into this control blow-up. And the statement is that, let me call this delta log, and the conormal bundle of delta log is omega X log. Okay? So you can reconstruct geometrically the logarithmic differential forms by doing a certain operation which is of geometric origin on the diagonal. Now, if you have that, then you can basically mimic the definition of Cauchy homology, now looking at not the derived self-intersection of a diagonal, but rather the derived self-intersection of a non-diagonal. So you can define THH of A, comma M as the derived self-intersection of the log diagonal in the above sense. There is an explicit formula, which is not really useful to write down at the moment, but the geometry is this, right? So the explicit formula, slash definition, was due to John Brockness. Although, as far as I know, he did not observe that you had this sort of geometric interpretation, as I explained. Okay? So just wrote down something, and then you can posteriori recognize that what he did can be interpreted logically, as I said. Okay, so okay. So first of all, this interpretation tells you that logarithmic THH is intimately related to logarithmic differential forms. So it's not outrageous to think that a logarithmic variant of the HKR theorem would hold. Okay, so
You see, what's the underlying scheme of this X?
right. So X is in this case X would be a log gadget, and when I say X underline, I mean I forget the logarithmic structure.
So the product is just as a
That would be the classical product of schemes, and that would be another thing, which is a scheme, okay, which is obtained by.
It's not the product in the log in the flow.
So since you know log geometry, this is the exactification of a diagonal map.
My question was, what is the underlying classical scheme of X times X tilde?
It's a affine chart. It's an affine piece of a blow-up of X times X. That's why it's a blow-up. We can write it down as a blow-up, and it is actually a blow-up. Okay? And it is. I mean, it's an affine chart of a blow-up. If you knew log geometry before today, then you can say that this operation is what I told Bruno. So it's the exactification of a diagonal. If you don't know log geometry, then this doesn't really help much probably, and you can use my description in a rather indirect way. Okay, so right. So similarly, you can define derivates, right? You can define things like TT of A comma M. You can define TC minus of A comma M. Okay, and so on and so forth, because you can actually show that this thing also carries, and it is also not completely obvious, an S1 action. Okay? This is less obvious than the classical definition of topological action homology, because while it is somehow clear in the formulas for definition of THH that there is an S1 action, if you do now this self-intersection on something which is not a product, it's much less clear why this should carry also an S1 action. In fact, it's a cyclotomic spectrum if you know what the cyclotomic spectrum is. But anyway, so let me say then the following theorem. So this is self again Medici back. So let RP be let's see, a regular regular, log regular, and this is something with an it's a bit technical, but the e.g. R is R comma P is the sort of local model for a semi-stable family. Okay, but I mean, technically speaking, you can be more general than that. Is the sort of a logarithmic analog of regularity. There is such a notion. This is also due to Kato. ZPI. Right? And assume that RP is vertical, i.e., the logarithmic structure is concentrated in say P equals 0, the fiber D. So again, this is everything is satisfied in the case of a local model of a semi-stable family. Right? So it's this R will be the ring of coordinates of your semi-stable family. So something like ZP x1 xn modulo x product of xi's minus P, and the log structure will be say free, so a monoid. N to the R, where R is the number of coordinates that appears in the idea. Yeah? Sending EI to XI. Right? Yeah, so something very concrete. Then, here the following. So PC of R P, PC down P, P, here you have PC of R P, P, PC of R mod P. It's Cartesian. Okay. Right. So the top line of the square is the square. It's the thing which kind of appears in the values of the square. Not exactly, okay, because there I had HT and HC minus, but in any case, conceptually, you had something related to TC of R and TC of R and P, and then you have to sort of juggle around with that. And on the bottom, I have logarithmic invariance. Okay? This is telling you that somehow the this integral gadget can be reconstructed by the mod P guy plus the log lift, okay, in this comparison, yeah, in the reduction mod P comparison. So this the proof of this fact is by induction on the rank of P, okay. You can reduce to the case where P is a free monoid, and then you can do induction of rank of P, and builds on the following fundamental result, which is the existence of sort of Gaussian or residue sequences for this kind of invariant, right? So key result is the fact that, so we say alpha. Okay, so suppose that you have a free monoid, okay? Suppose you're in this situation, and you can reduce this equation by a bit of Eiffel descent. Then there is a sequence like this, HC of R half of X. Fiber sequence. This is a fiber sequence. Okay, so how to understand this sequence? All right. Okay, so let's think for a second, okay, that I can replace my invariance with things really given by differential forms. And that D is equal to 1. So example. Example / intuition. D is 1. Okay. And pass to iterations. Okay, so first of all, it's not really relevant to work with HC. You can work with HP, with HH, with any variant of auction homology that we introduced before. Okay, so the same sequence would exist for all these variants, and also for the topological variants. So it's really a uniform kind of statement. Okay. All right, so if I pass the filtrations, then and D is equal to 1, then D minus 1 is 0. There is no log structure here. This will be something which looks like differential forms on R. Let me start from this. Right? So you have something like omega star of R. Okay? Here, okay, I have these one, and omega star gets replaced to logarithmic differential forms, right? So I have omega star and omega star R log on, say, X. Yeah? So it will be differential forms with log poles along X, which of course contain differential forms, right? Regular differential forms, logarithmic differential forms. And when you were in high school, you learned that if you have logarithmic differential forms, so you have a form of, you have something like dx over x, or if you have a form like this, you can take a residue, right, of your form at the pole x equals 0. And this lives as degree minus 1 on R mod x, right? Here it is. Of course, if you have to shift this there, you have a shift by 1, and the shift by 1 would appear in the differential terms. Okay, so the way so this kind of result was originally proven by Rognes, Agave, and Lichtrul. But follows now from the existence of, well, rather say, from the homotopy purity theorem, for non-A1 invariant logarithmic motifs. So the idea here is that five minutes. Okay, so the idea is that there is a version, there is a variant of SH, okay, the stable motivic homotopy category, in which building blocks are log schemes, and the homotopy purity of Morel-Verbotsky is replaced by suitable version giving something like this. Okay, so I should stress that the invariants like TC, HC, TP, everything constructed out of auction homology, differential forms are not representable in the Verbotsky's SH, because those are all examples of known A1 homotopy invariant homology theories. Nevertheless, they admit logarithmic extensions, which I define here, and as such, they are all representable in this variant of SH. And the structural result, which is typically true, you can prove in the category, they give you for free this kind of fiber sequence. Okay? And this fiber sequence is extremely useful because it allows you to do induction of the rank of monoid. Okay? And you go back to, so you do induction of the rank of monoid and the dimension of the ring, which you need to do them simultaneously, right? Because this, here the ring stays fixed, but the monoid increases. Here you have both of them are going down, right? The dimension and the rank of the monoid. And somehow then you can sort of reduce to the case, but there is no log structure in which in this case the safety is stripped, right? There is nothing. So that's more or less the idea. And maybe let me just finish by saying that, yeah, so the log version of the Cauchy constant Rosenberg theorem, this is due to myself, Buson and Polan Esper. By the way, yeah, this was developed in joint work with Polan and Buson, and Buson also has some work by himself in which he sort of generalizes our results over more general days and includes the language, sort of, yeah, more general results. Right, so the log version of HKR tells you that a sort of HP and HC minus are related respectively to log the RAM and Hodge-Filter log the RAM homology. And if we combine this with that and with the base on Hubble square in the non-log case, so you do this kind of induction and use also some other results which invoke the fact that you can also construct these logarithmic invariants using something called the infinite root cycle, these three tuples, some other thing, which I don't have time to talk about. Anyway, using a lot of stuff, you can actually conclude and write down a square which looks like the Bayesian Hubble square when you're making Moore-Nicolaus, which on the top you still have K-theory, like continuous K-theory, and K-theory of the special fiber, and on the bottom you have relative logarithmic HC minus and HP, which allows you to prove if there's homotopy groups and use this log version of HKR theorem to prove the deformation problem I stated before. Okay, so I think I gave enough material, and so I stop here. Okay, thank you very much.
Yeah, awesome. Thank you very much. More questions?
Yes. One is about the theorem of Grundemo-Nerichkar. How is that raised? That is being raised. About the existence of Yodo-Kato-Chernow-Kara.
So right. So the way we prove it is by
Okay.
Right.
How we prove that also compatibility.
Compatibility.
Yes. Does it have some compatibility? Because it's just, of course, you have also, you may have also the, because it's starting from the special fiber going to the option, yourself to the Yodo-Kato theorem. Or the Yodo-Kato.
Yes. Yeah.
But you can also take the spectrum of the generic fiber and how you can you make some compatibilities with the Bayesian?
Which kind of compatibility do you want?
Just because the fact that the Yodo-Kato cohomology is isomorphic to the generic.
Yeah, depends on the genetic generic fiber. Yes.
So if you have naturally you have from the K theory of the generic fiber to the special one.
No.
Okay, so you don't have any kind.
No, not really. It's a bit. It's actually quite magic because you start from, the way we prove it is by, abstract orientability theorems. So the fact that the Yellow-Kato homology has description in terms of log derivate, and then you prove formally that log derivate homology is representable in log SH, and then it's orientable. It's it has a projective bundle formula, so you get formally a Chern character. But as you see, it comes from a theory of a singular variety with no log structure. It's really the underlying gadget to the RAM homology, to the Yellow-Kato homology.
And then you have the monotony, right?
Yes, it's automatically. It's automatically in the sub locus n equals 0.
Okay.
Yeah. It's automatically there. This is easy. Because you guess it's easy. So it's easy. How do you do it? Okay, so you need to know this for the first Chern class, and if you know this for the first Chern class, then you automatically get it for all the exactly for the Chern character, and for the first Chern class. For first Chern class, it was proven by Yamashita. Yes, in some sense. Because you can give a valid proof nowadays, but let me just put him. So.
So in definition of the log rings, say for example the generator CXY, how should I interpret this different code in place? So it means that
what Bruno said. So in one of them you're allowed to take. So you want a geometric or an algebraic interpretation. So for example, let's say that you have zx comma y, okay, and the log structure is given by n sending 1 to x. Okay, that's a well-defined example. So this is the variable in which you're allowed to take denominators. So here you have omega of zx y comma n, okay, over z. Okay, this is free, and the base is given by dx over x and dy. Okay, so you have this symbol, you have of course. You have also dx, right? Because dx is obtained by x times dx over x. But you have strictly more than classical differentials. Geometrically,
I would say that simply as a fine space. The set there's a level of differential that you have more. You have the log differential.
So geometrically, if you don't want to talk about differentials, okay, there is the following interpretation which I really love. Take all the complex numbers. Okay, so you have construction of so-called Kato-Nakayama spaces. Okay, so this is the algebra geometric. Okay, the idea is log schemes are the algebra geometric analog of manifold with boundary. So the Kato-Nakayama space attached to a log scheme is something like this. So let me just give you an example, not the general definition, which is a bit complicated. But let me take P1, okay? So P1 over C. Okay? And take the vectorization, right? So it looks like S2, right? The vectorization of P1 is S2. Okay? Then a log structure on this is like specifying, in this description, is like specifying a close point on P1. It's not a close point, but let's say a single close point. Okay? So you have something like n. So locally on an affine chart, you have something like n or a1 in the variable, say x, and sending again, right? 1 to x. Okay? Now, let's say that this is a chart in the neighborhood of the point at infinity. And point at infinity is this one. Okay? So the log gadget is something which sits between A1 and P1. Right? So how's the tip in between? So the complex realization of A1 would be S2 minus a point. So this contains, right, minus this point. Now this is an open manifold, right? I'm going to remove the point, right, from the manifold. So I mean, it's a legit operation. Sorry? And what you're doing here is, you're spoiling me. So what you're doing here is rather doing something like this. So here you replace this point, okay, with a small circle around that point, so which you attach as an S1. Okay? So there's an S1 which is drawn in a small neighborhood of infinity in S2. Okay? So you pinch this hole, you enlarge it a bit, and then you sort of take this as a gadget with boundary. So this is no longer a manifold, doesn't live in the realm of manifolds. S1 does, S2 does, S2 minus a point does. This is something, this would be the complex point attached to this gadget here. Okay? So here, in the neighborhood of this point, of course, you have something like r greater or equal to 0, right? That's a child times, times an interval. Yeah? So this would be your little description of your manifold. So you have a corner, okay? You have a manifold with corner. And you can generalize this picture, okay? So this is called the real Laurent blow up of that thing at the point where the log structure is constructed. So, real Laurent blow up. Okay.